Okay, we'll get back to section 11.2 here. We just looked at the harmonic series, which is the summation as n equals 1 to infinity, 1 over n. That's a divergent series. Okay. Here's a statement next. Let the summation as n equals 1 to infinity of a sub n be equal to a, and the summation as n equals 1 to infinity of b sub n equal b. Okay, so I got two series, and they do exist. Okay, so you're not going to get infinity or negative infinity. Then if you have the summation as n equals 1 to infinity of a constant times a sub n, constants can come out of summation signs. Okay, so that'd be the constant times the summation as n equals 1 to infinity of a sub n, that's a. So you get the constant times a. The next thing, so the summation as n equals 1 to infinity of a sub n plus or minus b sub n. I can split that summation into two summations, and the summation as n equals 1 to infinity of a sub n plus or minus the summation as n equals 1 to infinity of b sub n, that's equal to a plus or minus b. Okay, so those are going to be handy to know. There's a couple of theorems next here that we'll talk about. Theorem 1 says that if the summation as n equals 1 to infinity of a sub n converges, then the limit as n approaches infinity of the sequence a sub n is equal to 0. Okay? There's a note there that says you cannot read this right to left. Some students tend to do that. Don't do that. Okay? So if the limit as n approaches infinity of a sub n is equal to 0, then the series given by the summation as n equals 1 to infinity of a sub n might converge or it might diverge. We don't know. Okay, so and like here's an example. The harmonic series. Okay, if I look at the limit as n approaches infinity of 1 over n, that's equal to 0. Okay, but I got a divergent series, right? We've already said that. And over here, the very first example that I showed you in this section, if you look at the limit as n approaches infinity of 1 divided by 2 to the n, that is 0. Okay, but this series converges. Okay, so in other words, that like just because the limit as n approaches infinity of a sub n is 0, that tells us nothing. Okay, so now if you got a convergent series, then the limit as n approaches infinity of a sub n is equal to 0. That will always happen. Okay. Theorem 2 is going to be really important to us. And we sometimes call it Theorem 2 the divergence test. Now, the reason I say it's going to be really important is because in the next couple of sections here, we're going to be looking at a whole slew of tests for determining convergence or divergence for a series. Okay, so this one's called the divergence test. Okay, it says that if the limit as n approaches infinity of the sequence a sub n is not 0, then the summation as n equals 1 to infinity of a sub n diverges. That will always happen. Okay? Now, if you switch the statements, if you get a divergent series, that doesn't mean anything. Like you can't necessarily assume that the limit as n approaches infinity of a sub n is not 0, right? Here's an example. The limit as n approaches infinity of 1 over n, that's equal to 0. Okay? So again, don't read this, backwards here, right to left. Read it left to right. Okay? Let's look at a proof of and by the way, so Theorem 2 is the contrapositive of Theorem 1. So I said that in Theorem 1, you can't just switch both sides and have it be true. If you switch both sides and negate both sides, that's where theorem 2 comes into play. Okay, so if the limit as n approaches infinity of a sub n is not 0, then the series given by the sum as n equals 1 to infinity of a sub n diverges. That is true. Okay, and that's the divergence test. Okay, we'll look at plenty of examples of where we're using the divergence test here coming up. Let's look at a proof of statement 1, though. So if I look at the nth partial sum, which is a sub 1 plus a sub 2 plus a sub 3 plus all the way up to a sub n, then a sub n, let's see if I were to solve this equation for a sub n, that's equal to s sub n, and I'm subtracting all n minus 1 of these terms. That would be the nth partial sum, or the n minus first partial sum, okay? So I'd be subtracting s sub n minus 1, which is a sub n, okay? Now, the summation as n equals 1 to infinity of a sub n converges, right? We can assume that's true. We have to show that the limit as n approaches infinity of a sub n is 0, okay? Now, if this series converges, then I know that the limit as n approaches infinity of the nth partial sum exists. That's by definition, okay? So because it exists, suppose that the limit as n approaches infinity of s sub n is s, okay? And I'm not getting infinity or negative infinity. It's going to be some number, s. Then the limit as n approaches infinity of s sub n minus 1, that is also equal to s. Why is that? Well, because all the previous terms have to converge, and they're going to converge to the same value, right? So if it's not going to matter if I look at the first n terms or the first n minus 1 terms. All the terms are going to infinity, right? And so you're going to get s, whatever s is. Now the limit as n approaches infinity of a sub n, that would be equal to the limit as n approaches infinity of s sub n minus s sub n minus 1. The limit of a difference is the difference of the limits. The limit as n approaches infinity of s sub n, that's s. And the limit as n approaches infinity of s sub n minus 1, that's s. S minus s is 0. Okay, but that's where I had to get to. I had to show that the limit as n approaches infinity of a sub n is 0. Okay. When we take a look at this next example here, so suppose that I have a sequence a sub n where a sub n is n cubed minus 1 divided by 3n cubed plus 2n squared. And we'll do part A and part B here. So part A, determine if the sequence a sub n is convergent. Okay. Well, to know if that converges or not, I need to find the limit as n approaches infinity of a sub n. So that's equal to the limit as n approaches infinity of n cubed minus 1 divided by 3n cubed plus 2n squared. And let's see, I can use L'Hopital's rule if I want, or if I multiply the top and bottom by 1 over n cubed. There's no harm with doing that, right? I'm just multiplying this by 1. I'm not going to change anything. Then that would be the limit as n approaches infinity of 1 minus 1 over n cubed divided by 3 plus 2 over n. N is approaching infinity. So the limit as n approaches infinity of 1 over n cubed, that's 0. And the limit as n approaches infinity of 2 over n, that's 0. Limit of a constant is always a constant, so I got 1/3. And yeah, so if I were to list out all these terms, okay, it's going to be getting closer and closer to 1/3. That's what I'm saying. Okay, now part B, determine if the series, which is given by the sum as n equals 1 to infinity of a sub n, is convergent. Okay, so the series, that's different. Now, so if I list out all the terms, I'm getting closer and closer to 1/3. Now, what if I add up all infinitely many of the terms? what's the grand total there? Okay, that's what we're saying in part B. So in part B, we're going to use the divergence test. The limit as n approaches infinity of a sub n, that's 1/3, which is not 0. And remember the divergence test here. It says if the limit as n approaches infinity of the sequence is not 0, then the series is divergent. Okay, so that implies that the series given by the sum as n equals 1 to infinity of a sub n, that's a divergent series by the divergence test. Okay, now I really like this example because it should hopefully describe the difference between a sequence and a series. Okay, in a sequence, all I'm doing is listing out a bunch of numbers. And I'm going to see where that list goes as I head towards infinity. But with a series, I'm adding up all the numbers. That's a different problem. Okay, so if I add up all infinitely many of these numbers, what's the grand total with that? Well, with this one, I'm going to get infinity. Okay, if I add up all infinitely many of these numbers here. Okay, that's what we're saying. So we got a divergent series. All right. I've got some more examples here. We're going to check if the series is convergent or divergent. And when we do that in the next video here, so let's see, in the next video I'll pick up with this example here. Okay.